So this is the first of the list of important big O examples that I posted onto D2L. So basically what this is saying is any polynomial of this form, which you know from college algebra, this is what we call polynomials. So we have a real number times x to the n, another real number times x to the n minus 1, so on and so forth, down to a real number times x plus another real number. And I also want to note that a to the n is not going to be 0. That's another condition that needs to be added to that. But basically, that an n-degree polynomial is big O of n. So it's pretty straightforward to show this is true. And it uses something called the triangle inequality. And the triangle inequality basically says that if you have any two real numbers, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. So you can play around with that with different values for a and b. And try it with both positives, try it with both of them negative, try it one positive, one negative, one of them 0. And the proof that it works in general is pretty straightforward and pretty simple. It's just tedious to do. And there's a skeleton of it in the book, and I'm thinking about making this a extra credit assignment. Making an extra credit assignment to fill in the details to show that that's going to be true. But we have to apply this triangle inequality over and over and over a couple times. So let me shrink this down a little bit and put it up here. So we're going to start with just the absolute value of an xn plus a n minus 1 x to the n minus 1 so forth to a1x plus a0. So just copy down what the polynomial is. So we'll apply the triangle inequality n plus 1 times. So this expression is going to be less than or equal to absolute an x to the n plus absolute a n minus 1 x to the n minus 1, so on and so forth until we get absolute a1x plus absolute a0. So now what we're going to do is factor out x to the n out of all of these terms. So this is going to be less than or equal to x to the n. Actually, since I'm just factoring, this is going to be exactly equal to x to the n times the absolute value of an plus the absolute value of an minus 1 over x plus, and if I keep doing that, it's going to end up with the absolute value of a1. Oops, let me fix that mistake. The absolute value of a1 over x to the n minus 1 plus the absolute value of a0 over x to the n. And I can say this is true, and I can go ahead and drop the absolute values on my x's as long as I stipulate that if x is bigger than 0. Rather, x is bigger than 1. So that's going to give us pretty much everything we need yeah, this gets us everywhere, because since we assumed that x is bigger than 1, that means that this bit right here, this expression right here, this is going to be less than or equal to x to the n times the absolute value of an plus the absolute value of a n minus 1 plus down to absolute value of a 1 plus absolute value of a 0. And that's everything, because we chose, or we noted that x had to be bigger than 1 right there, so that means that if x is bigger than 1, we have that our function f of x is less than or equal to c times x to the n, where in this case c is equal to the sum of all those constants, absolute a to the n plus absolute a n minus 1 plus a 1 plus a 0. Now, I'm sure that everybody in the class can follow this if you spend enough time looking at it, but it's enough just to be able to use it. So we can take it as a given from now on that this is true, that an nth degree polynomial is big O of x to the n. That's something that you can use freely when you're doing some examples. And I'm going to do some examples at the very end of this video. Here's another one that's really useful. And the example out of the book says, how can big O notation be used to estimate the sum of the first n positive integers? So what we're going to do is we're going to just define a function f of n that'll just be 1 plus 2 plus 3 plus out to n. So watch what happens. As long as n is greater than 1, we're going to get that this expression right here, 1 plus 2 plus 3 plus n, is less than or equal to n plus n plus n plus n, where we're summing this n times. Okay, all I did was I replaced all the numbers with n's. This 1 got replaced with n, this 2 got replaced with this n, this 3 got replaced with this n, and so on and so forth until we get to the very end. And all of this is equal to, so what I'm going to do is, well, I mean, this whole thing is equal to n squared. If you can't see that directly, look at it like this. If you factor in n out everywhere, you have n times 1 plus 1 plus 1, where we're adding up n times. The sum is n times. So that's just n times n, or n squared. So what this shows is that the sum of the first n positive integers, if we just let n be bigger than 1, this sum is less than or equal to n squared. So what we get from that is that this function f of n is big O of n squared, with k equal to 1 and c equal to 1. Alright, this next one, the first bit of it just explains, in case you forgot, what n factorial is. It's n factorial is 1 times 2 times 3 up to times n. And, you know, and we define 0 factorial to be 1 for several reasons that we'll actually get into when we get into the section on combinatorics and counting. But some examples: 1 factorial is 1, 2 factorial is 1 times 2, or 2, so on and so forth. And it also notes that this factorial function grows really fast. 20 factorial is this big, huge number right here. So how can we give a big O estimate of factorial? Well, let's just notice that n factorial is 1 times 2 times 3 times 4 up through times n. But this is going to be less than or equal to n times n times n times n times n, where this multiplication happens n times. This is equal to n to the n. And what that shows is that whoops, that shows that n factorial is big O of n to the n, with k equal 1 and c equal 1. Now, taking this a little bit further, from the equation that n factorial is less than or equal to n to the n, if we take log of both sides, we'll get log of n factorial is less than or equal to log of n to the n, which is equal to n times log of n, because recall from college algebra, when you take the log of something raised to a power, that exponent jumps down to the front. So what this gives us then is that log of n factorial is big O of n log to the n. That last example gave us a big O estimate of log of n factorial. So now we're going to use this fact, that n is less than 2n whenever n is a positive integer, to show that log n is big O of n. Now, this idea that n is less than 2 to the n, this is something else that we'll prove in Chapter 5. I know it says 4 there, that's a mistake. In Chapter 5, because we have to do that by induction. So let's just take that as a given just for right now, and see what we can do with it. So if n is less than 2 to the n, I'm going to take log base 2 of both sides, and that'll give me log 2 of n. Actually, let me see if I can clean that up just a bit. Log base 2 of n is strictly less than n. Well, this tells us that log 2 of n is big O of n, just by taking k to be 1, say, and c to be 1. But what do we do about more general bases? If I don't want to just deal with log base 2 things, how can I deal with that? Well, in that case, we're going to use the change of base formula that, again, you learned in college algebra, that lets us write log base, I want that to be log base b of n. I can write that as log 2 of n divided by log 2 of b. And again, that's just applying the change of base formula. But because of this inequality right here, we can say that log base 2 of n over log base 2 of b is less than n divided by log 2 of b. So note that this is just a constant, okay? Because b was just an arbitrary base, and 2's a real number, so log base 2 of b is a real number. That's a constant. So we get that log b, where b can be any base you want, of n is O of n by taking k to be 1 and c to be 1 over log 2 of b. There's also this theorem, which gives us a way to give a big O estimate of the sum of two different functions. Now, at first I was going to do a proof of this, but the proof in the book is actually pretty good. So you can read the proof in the book, but basically it says if f of x is big O, if f1 of x is big O of g1, and f2 of x is big O of g2 of x, then the sum of those two functions, f1 plus f2 of x, is big O of the maximum of g1 of x and g2 of x. So I'm not going to prove this. You know, you can see the book if you want to see how this works. So see the book, because the proof in that is actually pretty good. So let's go on. Same here. You know, you can look at the proof in the book, but this follows immediately from the theorem before. If both of these two functions, g1 and g2, are big O of g of x, then f1 plus f2 of x is just big O of g of x. So again, see the book. And I'm going to say it one more time. For this, see the book. Because these are immediate from the definition, and it will be really good practice to kind of work these out for yourselves by looking at the proofs in the book. Now, this is the first of two examples that I'm going to go through that are going to help you do 27A and B. And to do these, you just use what you know about each individual function. That is, you know a big O estimate for 3 times n, you know a big O estimate for log of n factorial, and you know a big O estimate of n squared plus 3, and you know one for log of n. So all you do is you put all that information together using those previous 2 or 3 theorems about how to combine them together with sums and with products. So we'll start out by giving by finding big O of the first thing that's being added, 3n times log of n factorial. It's immediately clear, I think, that 3n is big O of n by taking k to be 1 and c to be 3. It just follows straight from the definition. And then one of the ones that we just worked out was that log of n factorial is big O of n log of n. So using that previous theorem that the you know, if you want to find big O of two things multiplied together, it's going to be big O of what bounds both of them. That is, if we take 3n times log of n factorial, this is going to be big O of the big O estimate for 3n times the big O estimate for log of n factorial. So if you put it together, 3n log of n factorial is big O of n squared log of n. So that takes care of this first part of the big entire function that we're trying to give a big O estimate of. So let's go ahead and move this up here to the side. We'll need that very last line a little bit later. Alright, so now let's look at the second part. Oh, wrong color. Let me fix that. N squared plus 3. This is less than or equal to n squared plus 3n squared, which is equal to 4n squared. So that means that n squared plus 3 is big O of n squared. And because of what we did previously, log of n is big O of n. And so since we're multiplying these together, that tells us that the whole thing, n squared plus 3 log of n, is O of n cubed. So what we just did was show that 3n log of n factorial is O of n squared log of n, and the quantity of n squared plus 3 times log of n is O of n cubed. So that means, from that one of the previous theorems, is that the function f of n, which is this plus this, is going to be big O of the maximum of these two bounding functions, n squared log of n and n cubed. So we need to figure out which one is bigger. So if we try to compare these two, on one side we have n squared log of n, and on the other side we have n cubed. But notice that n cubed, sorry, that was a mistake. Notice that n cubed is equal to n squared times n. So we have an n squared on this side and an n squared right here, and a log n and an n. But like I've said several times, log of n is less than n. So we get that the left-hand side is less than the right-hand side, which tells us that this function, f of n, which is the sum of those two parts, this is going to be big O of n cubed. And we finally come to this last one. Now, I want to give a big O estimate of f of x equals the quantity of x plus 1 times the log of the quantity of x squared plus 1 plus 3x squared. Now the only thing that's going to give us any difficulty is this piece right here, because we almost immediately get that x plus 1 is big O of x. It's just a polynomial. And 3x squared is big O of x squared, because again, it's just a polynomial. So for this last bit, or the last bit that's left, the log of x squared plus 1, notice that x squared plus 1 is less than or equal to x squared plus x squared, which is equal to 2x squared, as long as we ensure that x is bigger than 1. And of course that's going to give us our k in the end. But what that tells us is that the log of x squared plus 1 is less than or equal to the log of 2x squared, as long as we ensure x is bigger than 1. So now apply your log rules. This is going to be equal to log of 2 plus 2 log of x, which is less than or equal to log of x plus 2 log of x, which is 3 logs of x, as long as x is bigger than 2. So I want x to be bigger than 2, so I can make sure that log of 2 is smaller than log of x. So I guess I lied. This is actually going to be where our k comes from. I want x to be bigger than 2. So this gives us that log of x squared plus 1 is going to be big O of log of x. So here's putting everything together, or at least summing everything up. X plus 1 is big O of x, 3x squared is big O of x squared, and log of x squared plus 1 is big O of log of x. So then we use those two theorems from before to put all of this together to finally give the big O estimate for the entire function. So putting the first two parts together, that is log of x plus 1 and log of x squared plus 1, we're going to get that x plus 1 times log of x squared plus 1 is big O of the product of their two estimating functions. So big O of x, because x plus 1 is big O of x, and then I'll multiply that by log of x, because log of x squared plus 1 is big O of log of x. So the log of this one times this one is going to be big O of this times this. And then finally, similar to the last example we did, since x log of x is less than or equal to x squared for x bigger than 2, because that's the bound that we needed from before. The original function f of x is going to be big O of, well, it's the bigger of the two bounding functions for the different sums. So the sums are x plus 1 times log x squared plus 1 and 3x squared. So the two bounds we have are the the big estimating function of this first part is x times log of x, and the estimating function for the second part is x squared. And so the estimating function for the sum of those two parts is going to be the bigger of the two bounds, x squared and x times log of x. But since x times log of x is less than or equal to x squared, the function f of x is going to be big O of x squared. And that is the end.